So let us start today with the idea of families. Now, we understand the families can have various sizes, and of course the chance-driven element in these ideas is the question of the gender of the children. Now let's start with a very sanitized and simple problem. Say a family has two children. It is known that one of the two children is a boy. What are the chances that the other child is a boy? Pause and think about this for a moment and see whether you come up with an instinctive answer. Was it perhaps 1/2? Now, if you came up with such an answer, this is entirely reasonable. It is based upon a vague presumption that the genders of children are independent, whatever that means, and that the two sexes are equally likely. And therefore, if you're told that one child is a boy, then the gender of that child does not, in our intuitive understanding, affect the gender of the other child. And since then both sexes are equally likely of occurrence, then the chance of that child being a boy is 1 and 2. This sounds very reasonable. But before we accept this as an accurate answer, we should pause and think about this in terms of the abstract formulation that we built up. What is the probability space under consideration? What is the sample space of outcomes? What are the events of interest? And what is the probability measure? Before we come to a right understanding of what this particular question is asking. So let us start with the sample space. What is the space of idealized outcomes of this experiment? Well, it is natural to write down each sample point or idealized outcome of the experiment by listing the genders of the two children by age. Older child first, younger child next. To use B for boy and G for girl, and using a Gothic font to distinguish it from ordinary letters, we find that the sample space has got 4 outcomes in it, 4 sample points. The sample points are BB, older boy and younger boy, BG, older boy, younger girl, GB and GG. What now are the events of interest in this particular structure? Recall that events are subsets of the sample space. Now we are interested in the other child being a boy, and therefore the native event of interest to us is the event that both children are boys. Let us call this event A. Now there's only one sample point which will trigger A, and that sample point is when both children are boys. In other words, it's BB. And therefore A, the event of interest, is comprised of a single atomic event, a singleton, a set consisting of one sample point. Lurking in the background, and this is the information we're given about the problem, is another event, the event that there is a boy, or more accurately, there is at least one boy. Now, if you take a look at this in a hard, cold light, what this says is this excludes the possibility that both children are girls. And if we remove that particular sample point from the sample space, then the remaining 3 sample points are all triggers for this event. Let us call it B, that at least one child is a boy. And therefore, B is comprised of the sample points BB, BG, and GB. Excellent. We've got 2 elements of the probability space under control, the sample space and the events of interest. We now have to come to a probability measure, and naturally enough, we have a discrete setting, in fact a finite setting. It suffices to provide an atomic probability, a probability for each atom, each singleton set. And in this very natural setting, in this very sanitized setting, it is natural to assume that all atoms have got equal probability, to assign equal probability mass to each of the atomic sets consisting of BB alone, BG alone, GB alone, and GG alone. The moment we have these atomic probabilities, we can construct the probability for any set whatsoever by simply adding up the probabilities of the constituent atoms. Because this is a combinatorial setting, the resulting probabilities are going to depend only upon the number of elements in your sets and not on what the precise elements are. And therefore, the probability of the event A that both children are boys is simply 1 in 4, and the probability of the event B that there is at least one boy in the family is 3 in 4. A picture can sometimes help to make these abstract concepts a little more vivid. Right? So suppose we write down the 4 elements of the sample space in this stylized picture that I've shown you, color-coded to help us notice what the various elements are. I'm using red for the event A, and green subsumed within the red in the case of BB for the event B, that there's at least one boy. This now is a sample space. In this sample space, the chance of A occurring, because it is a combinatorial setting, is naturally 1 in 4. This is the unvarnished probability of A without any side information about the process at hand. But wait. We are now told something about the outcome of the experiment. We are told something about the family that is being observed. We are told that this particular family has at least one boy. This means that in the sample space that we started with, the sample point consisting of 2 girls is eschewed, is removed. It is as if the sample space were simplified by the expulsion, by expunging certain elements of the space. This is what the information on the side is providing us. It has reduced the space of possibilities. We now have 3 possibilities. It's as if our sample space has become this new event B. Now, given that B has occurred, we know now that only one of 3 possible outcomes can have occurred. And now we ask, what is the chance that A occurs? What is the chance the other child is a boy? What is the chance that both children are boys, given that there is at least one boy? This naturally resides at the intersection of these 2 events. The chance that there are 2 boys and that there is at least one boy is precisely the event that there are 2 boys. The event A in this case happens to be contained in, it's a subset of the event B. Naturally enough, the space of possibilities is reduced. Instead of 4, we now have 3. All of them happen to have equal chance. And therefore, the probability of observing that the other child is a boy, given that there is at least one boy, is the ratio of these 2. It is the proportional part of A that lies in B, colloquially speaking. And therefore, the chance we will ascribe naturally is 1 in 3, not 1 in 2, as we might naively have presumed. Here now is an example in a very simple setting of how side information can modulate underlying chances. A native chance of 1 in 2 has now become a chance of 1 in 3. Let's take a look at a slightly more complex example to drive home this point. And let us return to another old standby, dice.